We now record two very important results which are very useful for computing homology groups. So say we are given two spaces X and Y and they are homotopic to each other, then they have isomorphic homology groups. The second important point is, so say we are given a wedge sum of good spaces. So to more precisely understand good spaces, you can see corollary 2.25 of Hatcher on page 126. So it just says you have a space xi and a base point bi, then you have this wedge sum for reduced homology groups. This is iso to direct sum of homology groups of individual spaces. So if you have wedge sum, you just take direct sum and this will give you the homology directly. So this makes it possible to calculate homology of wedge sums really fast. Now we give example of two important spaces and we will use both these results to compute their homology groups. So the first space is given like this. It is a skeleton of a cube which consists just of vertices and edges. So only thing it has is vertices and it also has the edges, but it does not have the faces. So no faces in it. So this is how it will look like. This blue is the front face, this rust color is the back face, and then you have four edges which are connecting the front face to the back face. So first step is we contract these four edges in pink. So you get rid of these four edges. So we have the front face and the four edges in the back space are in rust color. Now we contract these two edges and this is what we get. You have the top face, bottom face, and the rest of the four edges. Then finally we contract, say, one of these spaces, these edges, and this is what we get. So you have all the four rust colors and then this edge is remaining. So you count this, you have 5 S1s wedged together. So S1 wedge with S1, wedge with S1. So 5 of them. So these two spaces are homotopic. So these two spaces are homotopic and therefore their homology groups are the same. So to compute the homology group of this is very easy. Now you just need to use direct sum. So first thing, notice that h0 of S1, this is integers, but we are working with reduced homology. So h0 of S1 is actually just zeros. And the homology group H1 of this space, so this is anyway not impacted by this tilde, only in the reduced space only 0 is impacted. This is not impacted. So this will just be H1 of individual spaces, which will just be integer, direct sum with integer, direct sum with integer, direct sum with integer, direct sum with integer. So you have 5 of them here, and for h2 and higher it is anyway 0. So this hi tilde is 0 for I greater or equal to 2. So this was easy to compute because we used these two results. Now we come to another example. So now we have a sphere. This is a sphere which is a shell is there. So it is not a skeleton, it's a sphere. I have drawn it so that we can see inside the sphere. So this is a sphere, a hollow sphere. So this is a hollow sphere. So obviously this is the construction in terms of CW complexes. It is made up of a 2 cell and a 0 cell. So you take the boundary of 2 cell and you attach it to 0 cell. So you get a hollow sphere. Inside the hollow sphere you have a hollow cube. So this cube is not a skeleton, it is the skeleton plus all the faces. So this is a hollow cube. So this is vertices, edges, and also faces. And each vertex of the cube is attached to the sphere. So each vertex of the cube is attached to the sphere. So there are 8 vertices of the cube, 4 on the top, 4 on the bottom. So you have 4 of these lines. So since we are going to take wedge product in the end, so we are going to take this hollow cube out. So this hollow cube is homotopic to a sphere. and this becomes a sphere. This sphere becomes this sphere, and all these 8 edges I bring it here. 1 2 3 4 5 6 7 8. So now what we do is we identify all these pink points to 1 point and all these pink points to 1 point. So if you do that, then these all of them will come to 1 point, and then you can homotope across one of these edges. So this one you can contract. So once you do that, if you contract this and you identify all of them to 1 point, this figure then becomes this. So this sphere comes here, this sphere comes here, and you have this wedge of circles. So this, you can see there are 7 circles here. 1 2 3 4 5 6 and 7. So you could have counted here only that there is 1 2 3 4 5 6 and 7. So all 7 of them are coming here. You're just contracting one of the edges. So once you have this, now you know this space is homotopically equivalent to this S2 wedge with S2 and then 7 of these S1s. Three, 4, 5, 6, and finally wedge with S1. So now homology of this space is very easy to find, because now you can use this result to find the homology of this space. Then you know the homologies of S2 and S1s, just take direct sum of it and we get the homology of this space.